Okay, we are happy because we have an excellent meeting. Your presence enhanced and enriched our meeting, our university, our country. But now we are all sad because we are almost finishing our Logic school. But we will have a fantastic end, and I'm very glad to announce my colleague, Walter Carnielli, who is going to present, to deliver the last talk, the last aula magna of our event. Carnielli is a well-known logician with several works in distinct areas in logic, but he will speak today about a subject that he is working during the last years, the last month, the last years. Carnielli was president of the Brazilian Logic Society, was the director of CLE for 2 or 3 times. He received several awards, and exactly this aula magna will present part of the results he has obtained recently, and it contains a paper that was just some weeks ago awarded the Newton da Costa Prize, the Brazilian Prize in Logic, relative to the year 2022, and this prize was awarded to Walter Carnielli and Juliana Bueno Soler. It was a joint paper, and so congratulations for both. And Walter, we are waiting for your talk.
Thank you very much, Itala. Thank you very much. It's a pleasure and an honor and an enormous responsibility to be able to give this last talk. And I try to make everything very simple. This has no much hard mathematics, but a bit different ideas that some people grasp it quickly, other people don't. I would like it that you be belonging to the first case. So I will explain it, the best in the more clear way I can. And the title is Paraconsistent Probability and Uncertainty, how a computer should reason about evidence. Not only a computer. I should have written here how a computer and how a philosopher should reason about the evidence. And this title reminds everyone about a paper by Belknap and Dunn about these famous four-value logic, how a computer should see, and this is his intention. Okay, so just to remind you, just to make it clear, because I have to say that, what's the role of paraconsistent reasoning? Paraconsistent is a philosophical position about the logical consequence, reflecting the law of ex contradiction, or ex contraddizione quadlibenti, or law of explosion. Then paraconsistent logic are useful to prevent human fallibility. Human or artificial intelligence agents make mistakes, maintain false beliefs or information, and reveal theories incoherently. So there are two main branches, the weak and strong paraconsistent logic, where the validity of the adjunctive and the non-adjunctive rules is essential. After all we have heard and listened in these 2 weeks, this seems to be absolutely stupid and obvious. But it has not been obvious. I have been working with paraconsistent since 35 years at least. And in the beginning, it was our dream to say that paraconsistency is useful to prevent human fallibility. Because people or artificial agents make mistakes. And then paraconsistent should be very useful to help correcting that mistake that people do. So nowadays, it's clear and it's obvious, but it took us years and years to arrive at this position philosophically. Okay? Why is that? Because artificial intelligence or paraconsistent logic is not really needed in pure mathematics. It is more needed in computer science, artificial intelligence, big data, and philosophy of science. Now, today, I'm going to show you that is also very useful, could be very interesting and useful for philosophy of science. I will be talking about what I call a paraconsistent Bayesian epistemology, which was the title of the paper of ours, which won this La Costa Prize. Okay, so I've tried to be clear and simple, but before anything, I like to make clear the idea of an adjunctive logic or adjunctive system or non-adjunctive system. This has to do with accepting or not that from A and B you derive or not the conjunction of A and B. When B is not A, in particular case when B is not A, non-adjunctive means that an agent can have contradictory beliefs, believing A and not A, but when it's non-adjunctive, but not believing in the contradiction of A or A. Or in other words, a non-adjunctive agent can maintain contradictory beliefs while avoiding to believe in a contradiction. But I don't want to take this position. This is a super easy position. And some people say that Stanisław Jaskowski logic is non-adjunctive, as Janusz Ciuciura has explained. This is not completely true. Parts of it can be read as non-adjunctive, but parts of it are not really non-adjunctive. So, adjunctivism, on the other hand, holds that if someone believes that A and believes that B, then he or she is committed to the conjunction of A and B. And we want to choose, we prefer to adopt an adjunctive logic, an adjunctive view, because in this way we could assign non-zero probability to contradictions. So it's important for me, or for our work, that we are taking for granted that logic should be adjunctive, right? And we are not afraid of adjunctivism, because a person can believe in A and not A, and can believe in the conjunction of A and not A, and not be trivial. Because our logic is paraconsistent, it does not sanction this principle of exclusion. And this should be obvious by now. So, for instance, a simple example, in an election poll with 1,000 people, suppose that 6% of the respondents prefer candidate A to B, while 70% prefer B to A. Then there is a 30% percentage of contradiction there. So I can measure it. And this would be completely different if you had only 5% of contradiction. So by taking seriously this adjunctive point of view, I permit that people can believe in contradictions, and using probability I can even measure how big or how complicated or how dangerous this contradiction can be. And this is an important point of our work here. Now, the most basic tenet of the LFIs, the logical formal inconsistent, is the following: that a contradiction is not the same as inconsistency. Right? Contradiction free, on the other hand, is not the same as consistency, which is written by using this black and white ball, the circle A. Okay? Now, it seems to be obvious at this point, but I would like to convince you. Some people are not convinced, they don't pay attention. They say all the time, it's inconsistent. What you should have to say, this is contradictory. And let me try to give you some examples to convince you. If I say, Lula is the father of Biden, and Lula is not the father of Biden, this is a completely obvious, a contradictory statement, because there is a negation there. I don't care if Lula is the father of Biden or not. I only know that this is a contradiction. On the other hand, if I say, Lula is the father of Biden, and Lula is the father of the Pope, this is inconsistent with the facts. There is no contradiction there. There is no symbol for negation there. You can say, oh, it's all the same. I know it's contradictory because I know the Pope. I know that the Pope is older than Lula. How can be the father of the Pope? Biden is older than Lula. How can be? Well, but that's not a logical problem. So it's inconsistent with the facts and not contradictory, right? This explains, so in a certain sense, you can think in the following terms. Inconsistent seems disharmonious, incongruous, disjointed, incoherent, like a sound, like if you hear me play violin. It's going to know what is incoherent sound, right? It's horrible. And so this is incoherent, incongruous, disharmonic, or whatever. There are several adjectives that can explain what's inconsistent. Right? On the other hand, contradictory requires a negation. Contradictoriness requires a negation. Right? It's a linguistic. It's a linguistic object. In a certain sense, it's a syntactic object. And an inconsistent is a semantic. Okay, contradictions are not all the same. So this is again is a second tenet of the spirit of the LFIs. A contradictory theory is not necessarily trivial, provided the contradiction does not refer to something consistent. So this is the spirit of this famous principle of the gentle explosion. So alpha and not alpha does not entail beta, but alpha and not alpha, for something which is known to be consistent, then it's explosive, right? So explosion only occurs in the presence of a consistent contradiction. And some people have such a difficult to understand that. Once I received a message saying, how can you say that you have a consistent contradiction? Contradictions are completely inconsistent. No, they are not, according to our internal philosophy of paraconsistency. No? So I hope this point is clear. It takes some time to some people to understand that. Okay, but anyway, we are going to be working in our now going to more formal items. My language contains then, because I'm going to be speaking about this L, let F, which is a logic of formal inconsistent and formal undeterminatedness. So it has negation, conjunction, disjunction, no sign for implication, a black ball and white ball, expressing consistency and inconsistency. So logically, it's a very simple system, nothing new here, only classical rules. I'm just deleting or removing some classical rules concerning explosion. Okay, so I'm not doing anything new here. I have this. Actually, this belongs to this FDE logic. This FDE logic. Everything is clear and classical here, and double negation, introduction, and removing or election. Now, the important point is to add these rules for this connective, for this new connectives here, right? If I have consistency and inconsistent, this is trivial. In other words, consistent is consistent. It's like if I had two white balls. I don't need that in the problem, but I could add it. Consistent is, it was born to be consistent by itself. So I'm assuming that the notion of a consistent is well behaved, is clear, is well done, is well defined, and etc., etc., etc. So, consistent, if I have something is consistent and inconsistent, this leads to an explosion. Also, from nothing, I mean, just like a tableau system, a K tableau, if you like, I have here either something is consistent or is inconsistent, even if tertium non-datur by itself does not hold for this logic. But for the consistent symbol, it does hold. Now, if I have alpha, not alpha, and alpha consistent, explodes, as the principle of gentle explosion represented here, and if something is consistent, then I restore this third value, or I mean this law of third valueness, right? Sense. right? I mean, I only have that in the presence of alpha being consistent, otherwise I don't have it. I mean, in other words, I restore tertium non datur in the presence of this consistency. Now, this let F is sound, complete, and decidable by 0-1 valuation semantics. Open problem, I don't know if it's finite value. If anyone could prove it, would deserve a note in Studia Lógica or other junior one, depending on how difficult it is. I tried, I couldn't find a proof that it's not finite value. So, it has this 0-1 valuation semantics. So, some advantages of the logic is that it is paraconsistent and paracomplete logic. Why? Because agents can believe in contradiction at the same time. They are not obliged to believe in all classical tautologies. It's a logic of freedom. Let F is able to express a distinction between a partial context where there is some positive evidence for alpha, but no evidence for non-alpha, from a second context where there is conclusive evidence for alpha. And so, alpha has been established as true, and no alpha is definitely rejected. How is that? The idea is that I can add evidence to something until I reach the point of conclusive evidence. So, I either have conclusive evidence or I have temporary evidence. So, this logic is able to distinguish between these two moments, having temporary conflicting evidence and arriving at the conclusive evidence where I have evidence for A, no more evidence for not A, because I have finished my procedure. And then, no, or vice versa, it's definitely rejected. This connective, consistent of the alpha, acts as classicality operator, a recovery operator. So, when consistent alpha holds, excluding middle and explosion are valid. That is, in the presence of consistency alpha, alpha and not alpha, then as I said, entails all possible beta. I restore here the principle of explosion. Although alpha and not alpha by themselves do not get to all possible beta. And again, consistent alpha restores this excluded middle, while it's missing here on alpha, while by itself, alpha and not the alpha is not in theory. So this is expressed by those rules here. Natural deduction rules that we can add. So as I said, they are here. So this is, I'm completing the system. Again, I'm making the mistake that Daniel Mundis made many times. This is completely anti-intuitive. This bottom here. You never know where you are. So, yes.
Do you have a non-deterministic semantics for this logic?
Yes. We have another deterministic semantics that was worked by Marcelo.
It is characterized by a 6-value matrix. In this sense, it would be finite.
Finite.
Yeah. In the sense, yes. I mean, finite in a non-deterministic element. Okay, in a sense. But if you, I mean, classical logicians will say, Lukashevich would say, yeah. It's not finite, it has to be
The
finite.
new matrices are the n matrices.
And what?
The new matrices are the non-deterministic.
Okay. Yeah, very possibly. New mathematics has a non-deterministic character. Okay, so this. Where am I? Okay, the following rules related to black ball and white ball can be proven. So alpha, this is important here. So you can prove the following. from a contradiction, a contradiction entails that an inconsistency, but not vice versa. How can you understand that philosophically? Is that inconsistent is much bigger than a contradiction. Contradiction is just part of an inconsistency. So if something is contradictory, okay, it belongs to the domain of inconsistency, reasoning or judgment or whatever, but not vice versa, right? And here again, if so either something is inconsistent or it is consistent, and then I restore excluding middle, okay? So, from the point of view of evidence, this rule R1 means that conflict evidence about alpha implies the non-classicality of the alpha, but consistent of the alpha does not imply the alpha and alpha. I just said that. And R2 exactly, it's written there, what I just said here with different words. Recovery modus ponens. This logic, modus ponens does not code for it, but again, in the presence of this consistent operator, I can define an implication, but not alpha or beta. Exactly, I mean, this behaves like an implication because in the presence of a consistent of the alpha, and alpha implies beta, I get beta, behaves as a legitimate implication, and I can recover the deduction theorem. The following form of deduction theorem rules: if I have consistency alpha and alpha, entails beta, implies that I can go to the other side and make it to behave like an implication, right? So in virtue of the rules, consistent alpha, and negation of the alpha, and also consistent of the alpha and inconsistent of the alpha are bottom particles, so I have a bottom particles. So, although, I mean, FED, not DFE, FDE. FDE has no theorem. There was a question that somebody made last time, and there was a certain confusion. Just to make it clear, FDE has no theorem, but let F does have a theorem. For instance, this one here, I can prove that consistency of alpha or not or inconsistent of alpha, etc. So let F has theorem. So it's important because it makes sense for my definition of probability. Now, how can I attach probability? This is a very simple schema, and using this schema you can attach probabilities to several logics. To Kashevich logics, to Gödel logics, even to intuitionistic logics, and many other things. How can you do that? Well, you plug the following four actions. Probability is a real value function from the language of logic to the real number, satisfying the following conditions. Probabilities are always between 0 and 1, meaning it's a 0, 1 closed in the interval. Tautologicity, if I prove something, then it has probability 1. If I had no theorems in my logic, it would make no sense to add this action, right? Anti-tautologicity, if something is a bottom particle, if it proves everything, is probability 0. Comparison, if the alpha entails beta, probability of the alpha is less or equal to probability of beta. And finite additivity that some people don't like, but it's enough for me here. Could I add infinity additivity, like Carnielli appreciates and Definetti does not? I could, but I don't need for the moment. In the future I can add it, working with this variant of a probability, as I call it, this philosopher's probability instead of mathematician's probability, makes things different, because I don't have here the Kolmogorovian attitude of a measured theory. Kolmogorov's idea is a measured theory. It's a mathematical theory very close to topology, for instance. But here it's completely different. Here, probability is completely connected to logic. It's another tradition. Today, are they equivalent? They are equivalent for classical logic. They are not obviously equivalent for non-classical logic. If you want to do Kolmogorov theory for non-classical logic, you need the equivalent of a sigma algebra. It's not going to be a sigma algebra, it would be a lambda algebra or something like that. You would need much more mathematical theory. We can do that. Yes, we can in principle using this RMPC logic, but not this one. Not this one here. So I have to be happy with the philosophers made by, the probability made by philosophers. Okay, this, using the, yeah.
What is the, can you go back a slide?
Yes,
No.
no, I never do.
So what, in anti-tautologicity, what does the alpha entails nothing mean?
Alpha entails everything, I mean, alpha entails anything.
Ah, okay.
Alpha entails any possible. Okay, that's a way to write this.
It's explosive.
So,
If alpha is explosive,
yeah, explosive, right. No, I can define conditional probability. I will be defining here conditional probability as P A given B, the probability of A and B divided by the probability of B if the probability of B is not zero, bigger than zero. So in terms of evidence, P of A given B means how much the evidence available for B affects the evidence for A. I'm measuring how much one evidence affects the other one. Can I use another definition of a conditional probability? Yes, we could. We could appeal to this Popper's probability and change everything and solve one important problem that people say that's a hard problem because P of B cannot be zero here, right? This is a zero point in definition of conditional probability. But for the moment, it's sufficient for us. The non-standard schema for probabilities also can be used to define paraconsistent possibility measures, not only probability, but also possibility measures. In the spirit of Didier Dubois and Rimgaard, where this possibility measure, possibility theory, is a kind of a rough estimate of probabilities, which is very useful for computer science because it avoids the problem of knowing in advance whether or not A and B are independent when I am going to compute the probability of A conjunction B. In possibility theory, the possibility measure of A and B is just the minimum. Okay, so it's a sort of a rough and quick estimate of measure of a probability or measure of a credence. As people say, credence calculus, that also works very well for non-classical logics. So, some nice theorems about probability, for instance, probability of alpha given beta and not alpha given beta, I have to take into account the conditional probability of an inconsistency of the alpha given beta in order to obtain the one. In classical theory, this is one without this part here. So I have to add some new object here to restore my computation of probabilities. Probability of beta given consistence of beta and not beta, consistence of beta is one. Probability, this is a very important point, very, very important point. Probability of alpha and not alpha is something between 0 and probability of inconsistency of alpha. It's not 0. That changes everything. Probability of alpha and not alpha is not 1, but this is something between 1 and probability of consistency alpha. If the probability of alpha consistency is 1 or inconsistency is 0, then I restore classical probability here. I completely restore. So, classical probability is a subcase, is a particular case of this probability when everything, better say in other words, when probability of a consistency is high, the highest possible, or probability of inconsistency is lowest possible. Okay? Again, this is classical probability of a consistency 1 minus inconsistent, and important to understand what this defined. This defined as a degree of consistency for alpha. Then I have a degree of consistency. Consistency can be measured, right? Where is here the PSAT problem that Marcelo Finger likes a lot? He's not here anymore. PSAT is again here. So PSAT, I have the the PSAT problem is also holds for this thing. I will be encountering this problem here again. And is it NLP complete? Yes, it's NLP complete as much as in classical case. So I have again all the same problems. That's very much like in this probability infrastructure logic, right? Am I right? Right. So it's hard, but not harder. And not even easier. Yeah. Which is a pity. Now I'm going to go into this Paraconsistent Bayesian epistemology. Okay. So the principle of conditionalization and how it can be expanded. The probability assigned to the hypothesis before receiving new evidence is called prior probability. So you have a certain prior probability, and then the afterwards probability is called posterior probability. Okay, and I think many people know that. But what's important here is the Bayesianism is not the only Bayes theorem. Bayes theorem is a kind of miracle. Why is it a miracle? Because it's so simple, it's so easy to prove it, it has so many deep consequences, and it has such a deep philosophical consequence. That's a kind of a miracle theorem, right? But it's not the only, Bayesianism is not the only Bayes theorem. Bayes theorem is a direct consequence of the definition of a conditional probability respecting the laws of probability. So, if you have just the definition of conditional probability, proof of the Bayes theorem is absolutely trivial. It's high school, or even less. So, I get P of H given E is a conditional probability. I just multiply and divide by this thing here, and then I get Bayes theorem. That's all. But the problem of the Bayes theorem is not to obtain it, how to use it. The use of it, which causes deep philosophical quarrels, difficult philosophical problems in the community. So this Bayesianism permits to make probability statements about data and the hypothesis, not only on data. I think this is very much clever, and this is very much useful. Because, in physical probability, not evidentialist or physicalist probability, you talk about dice and coins and things like that. You make hypotheses about events, but not probabilities about hypotheses themselves. So this here is a kind of a stochastic process that sort of reverses cause and effect. In terms of this Bayes theorem. Now, how is the Bayesian update working? Update belief in a hypothesis H in face of new evidence is expressed by the standard. I'm not being classical here, okay? The standard principle of conditionalization, which is not an action, but is a norm, a rule, or rather a rational modus operandi. We had some problems with the referee of our paper, because the referee said, how come that is not an action? It's not an action, it's a principle. It says how to use probability. It said the following. Posterior probability of H is the prior taking E into consideration. Or in other words, is the prior, previous measure of probability applying on H conjunction is E divided by the prior of E. The new one is based upon the old one. That's the way Bayesianism keeps updating the probability. And the big discussion is, do Bayesianists get closer to the truth or not? Some people say no, they don't. Some other people say yes, they will. They'll be closer and closer. And the problem is, this is one of the few methods we have to talk about induction. It's an inductive method in some sense. It's one of the few methods to talk about inductive reasoning, right? It's not an inductive logic, it's an inductive methodology. Okay, now, how can we then develop paraconsistent rules of conditionalization? Because I have consistent and contradiction are two different things that are not necessarily the same. Can they be made the same? Yes, if you add the extra action, saying that inconsistent coincides with contradiction, then you would have a new system which is closer to classical logic, but I don't want to do that here. I want to make them separate. So, the principle of conditionalization based on negation, on paraconsistent negation, is the following. The revising probability, revising P on the light of A is P of B and A. Before I have that one, now I'm just be subtracting here the probability of B and A and not A, and here the probability of A and not A, because now those guys are not necessarily zero. That's the only change we require. Can I prove that rule? No, I cannot, because they are not the axioms, they are not theorems, they are norms of reasoning. So we are proposing two new norms of reasoning. And those new norms of reasoning have some nice effect, as I'm going to show you. And this black ball pre-scont is exactly the same as before, but then I subtract the probability that B and A is inconsistent minus A being inconsistent. So I am supposing that only the problem occurs with A here, okay? Only A. So I have to be aware of this proviso here. Probability of A is bigger than A and not A, otherwise I get one impossible number here to divide. I get 0 or something less than 0. I don't want that, because my probabilities are numbers between 0 and 1, and here the same. So, negation pre-scont conditionalizing, taking into account the measure of contradictory information, while black ball pre-scont takes into account the measure of the non-classicality. They are not the same. Okay? They are not the same. Some theorem that we obtain here is those principles get closer to the standard principle as much as the evidence in favor of the classicality of A increases. This is completely intuitively understandable. If my probability of A gets close, bigger and bigger and bigger, close to 1, the consistency is closer to 1, everything gets closer to classical logic. Then those principles will be reducible, will be collapsing into the classical principle. And another theorem, those two guys, negation principle and black principle, get closer values again, as much as the evidence in favor of the classicality increase. So when we have this complicated scenario here, the classicality can be very low, and the principles give many completely different numbers, and if they get bigger and bigger, the evidence about classicality gets bigger and bigger, the two measures are getting together, and you'll be coinciding with the classical measure. So, this here, again, a proposition is normal, negation normal, if it's probability function P, if P of A bigger than 0, or A and black A bigger than 0 and 1. So, if A is not normal, P is a probability function. And if probability is consistent is 1, then P of not A given A is 0, and A given not A is 0, as a standard probability. Again, as much as I get closer to the highest possible consistency, B is getting closer and closer to this classical behavior. And if B is a probability function and A is not normal, then it's a probability function. Okay, well, this is not very important in this context. Those are principles that show only that my measure of probabilities is well defined and deserves a probabilistic citizenship. Okay? They behave like a probability theory would do. Okay. Now I base it upon those new conditionalization rules, as much as in classical case, then we can prove. Now, my first theorems appear. I mean, to prove theorems about conditional probability. The following theorem, the following forms of Bayes rules can be proven. If PA is bigger than BA and not A, and PB bigger than B and not B, then probability of B given A can be computed from A given B multiplied by this little animal here. Okay? I mean, again, I have a way of reversing, so to speak, cause and effect. Right? Reversing cause and effect. For two of them, for negation and for consistency. The same here, probability of BA in terms of black boy, or inconsistency, is A given B multiplied by this factor here, which is not zero and is, I mean, not zero, then it affects the computation in a completely nice way. Now, let me give you 2 examples, but actually I have prepared 3 examples. I'll give you the first one and the second, and I'll see if I have time to do the third one. So this is an example of, about an imprecise surveys and how this LETF can help to evaluate the effects of social media. Suppose an agency conducts 2 separate surveys about acceptance or rejection of a candidate K. This happened in Brazil all the time before the election. So they had completely crazy numbers and they did not know what to do with those numbers. And a political statement, I could not talk about that during the election because the right wing would say that probability had to be completely changed and Lula won the election because we're using the wrong probability theory. So I had to stop before, because it was really dangerous. So I was talking to some newspaper people in Folha de São Paulo and Estado de São Paulo. I offered myself to publish that. They said, no, please, don't do that now. It would be very dangerous. I'll show you why. Okay. So they are measuring the rejection or acceptance of a candidate K using the internet historical of users. And they find K's acceptance rate, P of A, is 0.4, and rejection, probability of not A, 0.8. How can it be? I mean, it's bigger than 1. How is this is understandable? Well, this is understandable because checking internet habits is not perfect. People sometimes do not see the videos. I mean, how much time I'm watching video for the right wing or left wing or whatever. This is a kind of correlation, not a perfect measurement. There's a correlation, and correlations are not perfect, right? People sometimes sleep during their looking at videos, or they don't care, or they lie, or whatever, or they leave the computer playing videos all day and don't pay attention to it. So there's a correlation on how much time you watch videos and your political attitude about accepting or rejecting. It can be contradictory. Okay, but they do another interview search to know who uses a certain social media T. Don't tell anyone, but T is for Telegram. Social media T is suspicious of spreading fake news, and it finds that only 30% of people admit they use it, while 85% say they never do. As you know, people lie, or don't say the truth on purpose or not, any reason. So probability of they watching this social media T is 0.3, and not watching is 0.85. Again, it's bigger than 1. Now, according to the survey, probability of EA plus not EA is bigger than 1. And also probability of T plus not, negation of T or looking to the social media or not is bigger than 1. So there's a conflicting evidence about A and T. So I have a paraconsistent scenario. I could also have a paracomplete scenario, but I will give you an example. I could have both at the same time. It makes computation much more complicated. That's why I'm choosing this one here. So considering that there are no gaps, probability of A or not A is 1, and T or not T is 1, and then the axiom of finite additivity gives probability of A and not A is just the excess, 0.2, but I need that before, I need to know that there is no gaps. And probability of T and not T is 0.15. Now, a third experiment, they also selected a control group of people who are real users of the social media T, and asking for their acceptance of the candidate K, they find a conditional probability here. This is the usual way of finding conditional probability. You don't have a logical way, you have to go and measure things. They find that the probability of A acceptance, given that a person is a user of this social media T, is 0.7. That is, the conditional probability of a heavy user of T to vote for K is very high. If someone is watching this social media, there's a very high probability that is supporting Mr. K. Who knows you are in Brazilian terms? I don't need to say with Mr. K here. So, question that the media would like to solve and nobody knows how to do. What's the probability of P of T given A? Probability that a person being influenced by the fake news of T, given that she is a supporter of Mr. K. Just apply the following, negation BT. So I have T given A is A given T multiplied by this factor, plug in the values here, 0.7, blah, 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 I obtain 0.52. This is, from my point of view, is a kind of a miracle of probability, of a new probability. Why is that so? Because, and it is an astonishing result. We prove that more than half of the people is more influenced by social networks and fake news than by judicial choice. But important point is that in standard probability, you cannot compute this. You have to throw away all these experiments because they have a contradiction. But using this new formula of probability, you can take profit of it. You can conclude something rational about it. See, this is, in my opinion, is a very important point to reflect. Okay, this is a, how much time I have? I have two more examples. Which count them is that?
10 minutes.
10 minutes. Then I only go to the second example very quickly. Second example, Pinocchio. Pinocchio is, come and meet Pinocchio. Pinocchio is sister of Pinocchio, but she's much smarter than he is, because her nose does not grow when she tells lies. Pinocchio is terrible. Pinocchio, the poor guy, when she tells a lie, his nose gets bigger and bigger, you know, everybody knows. Not for Pinocchio. So, you are rolling dice with Pinocchio. Now, suppose Pinocchio rolls a fair six-sided die without giving you any information. If she asks you about your unconditional credence that the die came up 4, suppose, or 5, whatever, which number you like, your rational answer would be 1/6, because it's a fair die. Right? She asks you about your belief, your unconditional credence, how much you believe that. If she tells the die came up even, your most rational attitude would be to update your prior hypothesis to a posterior F. Now, the degree of believing for, conditional on the new evidence, that's even, will be update your credence to 1/3, because she said you, okay, there are 6 possibilities. It's even. So the odds are out of context. Well, you can do these calculations here. You never find this. I did this explanation here. I mean, if you're going to see my slides, you can really compute it. Intuitively, it's obvious that is 1/3, but you can compute it. So any computer can compute it. That's why I say that is how computers and philosophers could think about evidence. Okay, but explain the calculation. So the calculation is explained here. I'm not going to lose time because this is obvious to most people. If you don't know how to compute it, our calculations are done. But the problem is, it happens, however, that Pinocchio lies sometimes. And you know that she has lied in 8% of the previous die games you played together. You have measured that and say, well, she's previously she has lied like 8% of the cases, the times, right? So in 8% of the cases, she says the die came up even when it actually came up odd or vice versa. Not always, because you see, if she were a perfect liar, that would be okay, fine. Perfect liars tell the truth, just reverse it. But she tells the lies sometimes with this measure. Now, standard conditionalization is not robust enough to withstand the contradictions and cannot be applied, but a paraconsistent conditionalization can be there, can compute through this negation prime con. In the present case, the hypothesis H behaves classically. I mean, the H in your hypothesis is classical. Probability of H and not H is 0. I mean, your die is fair. While P of even and not even concerning her information is 0.08. And then using this neg Price count gives you what the probability of H given E, taking into account that the prior is 1/6. I mean, you wanted the number 4 and it's even, is 1/6 as before, and probability of its lie is 0.08. It remains to evaluate H, E, and E. Okay, some sort of acceptable hypothesis tells you that they are independent events, and you can compute it, blah, blah, blah. So, you do the calculations, you compute the value that probability of H given E is 0.365. Now, it may be surprising to see that the paraconsistent update in this case is greater than the standard update. But this can be explained by the following reasoning. Whoever lies, lies to both sides. For or against the initial belief. It could be that the friend, Pinocchio, said odd and the outcome were even. In this case, instead of reducing the belief to 0, a prior belief should hold. So the larger value is a kind of aggregation, taking into account the symmetry of the situation involving lying. So, this is a baby example. Of course, we are still working on better example. And this is not the work of a statistician. This is the work of logicians. So I'm trying only to convince you that this makes sense. Okay? And then I have a third example. That's the classical confirmation theory, which is an important problem in philosophy of science. Namely the problem of the old evidence that shows that in certain cases, for instance, I will go very briefly, not going into the calculations, in certain cases, as in the case of Bayesian confirmation theory, I mean, there's a definition of confirmation which shows you that sometimes certain calculation has to be done in order for a new experiment confirms the theory, and it happens that in the case of Mercurio, when it was against the Newtonian mechanics, and theory of relativity explains that very well. But according to Bayesian epistemology, the amount of the number that they get was not rationally connected to the confirmation theory. So the confirmation theory is not working well in many cases for standard Bayesian epistemology or standard philosophy of science, because philosophy of science uses this a lot. And again, by using this new measure, we can find a way out of this dilemma. I don't have time to show it here. But again, it's a third example which shows that there is, in my opinion, lots of interesting possibilities connected to this. Okay. So, I go, I never know how to do that. That's incredibly wrong. So it helps not only the problem of perfect and the problem of all the evidence, but it also helps the problem called the perfect fit. It's explained in this enter of the encyclopedia, Bayesian epistemology, Stanford Encyclopedia. It's considered to be too demanding by admitting contradictory or incomplete evidence. So the perfect fit problem is the following. Probabilism demands that one's credence fit together nicely. For example, some credences are required to sum to exactly one and no more, no less, a perfect fit. We don't need here this perfect fit, so we also solve it or offer a solution out of this problem of a perfect fit. So why is this theory so exciting? So it's behaving, because of everything, I'll go very quickly because I don't have much time, right? It's encodes classical logic in the presence of a consistent. It's flexible enough to lead to an expansion of Bayesian epistemology. And I would like to say that this is part of an avant-premiere of a chapter of a forthcoming book by myself, Marcelo Cunillo and Abilio Rodriguez, with the assistance and collaboration of Enrique Antunes, that you are our student here, now he's a professor. He is going to appear in Synthesis Library, and the title tentatively is Contradiction of Evidence and Truth, Epistemic Interpretation of Paraconsistent. So a new book is arriving, Marcelo. Am I right? Yes. Thank you very much.
Yeah, could you please show the slide with Pinocchio with the computations?
Pinocchio computation. Let's see. Here, next one.
The next one, yes.
Yeah. This is done.
And the next.
Next.
Again?
Yeah, probably here. So here you say that this probability of saying E and not E is equal to the chance of Pinocchio mice. Yes?
Yeah.
But it's not greater than the probability of E, which is the probability of being even, yes? So it's not greater than one half. But what if Pinocchio lies in like in 60% of cases? Or in
Well, this is the bizarre problem. I have to find examples that fit my calculations. No all possible cases can be solved, right?
Well, I mean that this probability depends on how often Pinocchio lies, but it also depends, but it is upper bounded by a probability of E, which does not depend on how often Pinocchio lies.
Yeah,
I
no.
don't understand these connections.
Well, probability of E is 1/2, 0.5, right? And Pinocchio lies because she lies differently, so.
Well, for me, this implies that Pinocchio cannot lie in more than 50% of cases.
Oh, okay. Maybe my example is not perfect. I have to change the numbers. Yes, you're right. So, this is a bizarre problem. Requires a computer program to compute the real possibilities and to find the real adjustments of numbers in the examples. Yeah, you're right. Maybe I have to change it.
I can think of a couple of solutions. First of all, is to say that if she lies more than half the times, You just revert her answers and then she left less
Yeah,
than half
could
the
be.
times.
Yeah.
Otherwise, you could say that this formalization is not adequate because we are saying when we say the probability of E and not E, those have different meanings. One means that Pinocchio says it is even, and the other means that it is actually odd. So perhaps a more refined.
Yeah, it could be. I mean, I'm trying to give some motivating examples in order not to show only the logic of it, show that can be useful for some. But yeah, you're right. Maybe I have to. Actually, I need some nice and good postdoc student to work with that, and who knows a bit of programming and has interest in mathematics and philosophy. And I just take the opportunity to say that we have 4 positions open for postdocs, plus 2 additional ones. So if you ask me to compare, 6 positions open, and we are going to, Marcelo, perhaps in April we can make an international call, and it'll be asking for people to come and to help us, right? So that's a real big project, real big. Just Newport project.
So, okay, yeah, I agree. So the first solution seems to me less,
That's one possibility, yeah.
well, it's worse because E can be, well, an event with a very low probability, like 100.
Well, if, I can change the example to 0.4, then.
Yeah, well, okay. And the next small question, so you actually tried to use your formulas on real data, yes?
Yeah, no, not real data, inventing, I'm just inventing data.
Well,
I mean, not even Marcelo Figuer can get access to real data, I mean, no access. I'm not a statistician now, big data, computer scientist, just a poor, humble logician doing some conclusions.
But it would be interesting to, because you are making an assertion, like a factual assertion, that people have been more close to have been, so that could be tested.
Well, I'm just taking some examples that appear in the media. Nobody knows what to do with these numbers. I'm inventing some numbers that go correctly, more or less, to show that in principle, we can find some application. That's what I do. Otherwise, I could sell that, right? That was a perfect thing, I would never show you. I would sell to Amazon and to make a.
Another question?
Yes.
Yeah.
Here.
Yeah.
Yeah.
Is there a way to measure the predictions, the confiability of the predictions related to contradictions of data?
I don't know. This has to do with likelihood, this kind of things that I don't know much. In principle, yes. I mean, a competent statistician would gives you an answer. Unfortunately, I don't know. I think it's possible, but I don't know how to do it. I'm not working with this kind of. Other colleagues of us, like people in the University of São Paulo, or Julie Stern, and people that are working, or Marcelo Figuer maybe, but even Marcelo Figuer is not.
Another question? Comments? No? Well, thank you.